We have studied that there are mainly two types of DC generators, separately excited and self-excited. In this video, we will study characteristics of separately excited DC generator. There are three types of characteristics of DC generators. First is open circuit characteristic. It is between generated EMF EG and the field current IF. Second characteristic is called as internal or total characteristic between generated EMF E and armature current IA. And the third important characteristic is the external characteristic, which is drawn between the terminal voltage V and load current IL. Now the first characteristic is open circuit characteristic, OCC. So this characteristic shows the relationship between the field or exciting current, that is IF, and generated EMF at no load, that is EG, at a given constant speed. So on the x-axis there is field current IF, and on y-axis there is terminal voltage at no load, which is nothing but EG. Now this characteristic curve is also called as magnetization curve or no load saturation curve. Now while drawing the open circuit characteristic, we have to operate the generator at no load. Now at no load, the voltage drop in armature will be equal to 0, and therefore terminal voltage will be equal to EG. Now we have to increase the field current IF in steps from 0 to maximum, and for each IF we have to note down EG, that is terminal voltage across armature at no load. Now while performing this experiment, the speed of prime mover must be kept constant. So generally this speed is the rated speed of machine. Now here you know that Eg, it is proportional to phi if speed is constant, and the magnetic field strength or magnetizing force H, it is given by Ni upon L, and therefore H is proportional to I. In this case I is the field current IF, so H is proportional to IF. So if there is Eg on y-axis and IF on x-axis, then the curve is just similar to the BH curve, because Eg depends on B and H depends on IF, and therefore the curve is similar to the magnetization curve or BH curve for the material used for electromagnets. Now this curve, the shape is almost same for separately excited as well as for self-excited DC generators. So OCC is same for all generators, whether the generator is separately excited or self-excited. The second characteristic is internal or total characteristic. So the generated EMF in armature is EG, but actual available voltage across armature is always less than EG. It is because of the two types of voltage drops in armature. The first voltage drop is due to the resistance of armature, which is equal to Ia into Ra. And the second voltage drop is due to the armature reaction. We know that armature reaction is the effect of armature flux on main flux, and because of armature reaction there is demagnetization or reduction of main flux, and because of reduction of main flux there is reduction in the voltage across armature. So the EMF E is the EMF actually induced in the armature considering the demagnetizing effect of armature reaction only. So without considering the voltage drop in armature due to its resistance, that is IaRa, if only demagnetization effect of armature reaction is considered, then the EMF across brushes is E. So here E is equal to Eg minus voltage drop due to armature reaction. So if voltage drop due to armature reaction is subtracted from the generated EMF Eg, we get E. And that's why E is always less than Eg. Now if we plot this EMF E and current Ia, we get this internal or total characteristic. So this characteristic, it cannot be obtained experimentally because it is not possible to measure E with the help of voltmeter. But this characteristic is of interest mainly to the designer. But for practical applications, the characteristic which is important is the next characteristic, which is called as external characteristic. Now the external characteristic, it gives relationship between the terminal voltage V and the load current IL. Now the terminal voltage V can be obtained as V is equal to E minus Ia into Ra, where IaRa is voltage drop in armature, and therefore V is always less than E. Now as V is less than E, the external characteristic lies below the internal characteristic. External characteristic means characteristic between V and IL, and internal characteristic, as we have seen earlier, it is between E and Ia, and therefore external characteristic lies below the internal characteristic. Now this characteristic is very important because while selecting a generator for particular application, we have to consider external characteristic of generator only. Now this characteristic can be obtained by actually loading the generator from no load to full load in steps and taking simultaneous readings of terminal voltage V and load current IL. But while performing this test, we have to keep the speed and field current constant. Let us now see the open circuit characteristic of a separately excited DC generator. So this is the experimental setup to plot the OCC of separately excited generator. So here the generator is run with the help of prime mover at a constant speed. So here we have to maintain the speed of rotation constant, and normally the speed is maintained at rated speed. Now here the excitation is provided by separate independent DC supply because the type of generator is separately excited generator. Now this field current can be varied from 0 to maximum with the help of this potentiometer. Now the value of current flowing through the field winding, which is nothing but the field current IF. This current can be noted with the help of this ammeter, which is connected in series with the field winding. Now the terminal voltage of the generator at no load. So to record the generated voltage, voltmeter is connected across armature and the generator is operating at no load, and therefore the terminal voltage is equal to Eg because there is no voltage drop in armature as the generator is operating at no load, and therefore this voltmeter, it shows the generated EMF Eg. So we can increase this field current in steps, and for each field current we can note down the corresponding value of generated EMF Eg, and then we can plot the open circuit characteristic. On the x-axis we have to take field current IF in amperes, and on y-axis generated EMF Eg in volt. Then we can plot the open circuit characteristic of separately excited generator. Now we know the expression for Eg. Eg is given by phi Pn upon 60 into Z upon A. Now here speed n is maintained constant and all other terms are also constant, and therefore Eg is directly proportional to phi. So the generated EMF Eg is proportional to phi, that is flux per pole. So the EMF induced in armature, it depends on flux per pole which are produced by the field winding, and flux per pole depends on current flowing through the field winding, that is IF, and therefore as IF is increased, Eg also increases. So here with increase in field current IF, flux phi will increase and Eg also increases as shown by this open circuit characteristic. Now here we have to note some important points related to this OCC. Now when the field current IF is equal to 0, if there is no current in the field winding, then flux phi must be equal to 0. If phi is 0, then generated EMF is also equal to 0. But in this case, even if the field current IF is 0, the generated EMF is not equal to 0. When IF is 0, the generated EMF is equal to OA. So small EMF OA is induced in armature even if current in the field winding is equal to 0. So this is because of the property of magnetic material called as residual magnetism. So because of residual magnetism, the flux is not equal to 0. So some flux remains there even if the current in the field winding is reduced to zero. And because of that residual magnetic flux, small EMF is induced in the armature, which is equal to OA. Then up to point B, the curve is almost linear. That means as IF increases, EG also increases. So this is because up to point B, the reluctance of iron path is negligible as compared to the reluctance of air gap. And for air gap, the reluctance is always constant. So as the reluctance is constant, as the current is increased, then there is increase in flux, and because of increase in flux, there is increase in induced EMF EG, and therefore the curve is linear up to point B. But after point B, the reluctance of iron path cannot be neglected, and therefore the curve bends. And after point C, the filled poles get saturated. And after saturation of filled poles, even if the field current is increased, flux will not increase. And because of constant flux, this Eg will also remain almost constant. So beyond point C, generated EMF Eg remains constant. Let us now see the internal and external characteristic of a separately excited DC generator. This is the experimental setup to plot the external characteristic of a separately excited generator. Now here the machine is operated at constant speed, and normally it is the rated load. The current through the field winding is also maintained constant. So in this case, field current IF must be constant and speed N must be constant. Now the load is gradually increased in steps. So the load is variable and it is gradually increased from no load to full load. The current flowing through the load IL can be recorded with the help of this ammeter, which is connected in series with load. For each load current IL, we can note down the corresponding value of terminal voltage V. Terminal voltage V can be recorded by a voltmeter which is connected in parallel with armature. Now from the readings of ammeter and voltmeter, that is from IL and V, we can plot the external characteristic. Now this external characteristic, it indicates how the terminal voltage V changes as there is increase in load from 0 to maximum, while the speed and field current are constant. And that's why this characteristic is very important, because it shows the variation of terminal voltage V with change in load. So here, as the generator is separately excited, the field winding is excited by separate independent source of power, and therefore this field current is not dependent on the load current. So even if there is change in load, the field current will remain constant, and therefore the flux is also constant. Now, if the voltage drop in armature IARA and voltage drop due to armature reaction in the generator, if both these drops are neglected, then this terminal voltage V will be equal to Eg. And as flux is constant, speed is constant, Eg will also remain constant from no load to full load. So this is shown by this characteristic curve 1. So this characteristic curve 1 is the ideal characteristic. So in this case, terminal voltage will remain constant from no load to full load because the voltage drop in armature IARA is neglected, as well as the voltage drop due to armature reaction is neglected, and therefore this curve 1 is the ideal characteristic. However, in a practical generator, whenever the generator is loaded, current flows through armature. So armature also produce flux, and there is effect of armature flux on main flux. We call it as armature reaction. And because of armature reaction, there is demagnetization of main flux and there is reduction in voltage. And therefore, if armature reaction effect is considered, then the characteristic cannot be ideal. In this case, the characteristic will be slightly drooping as shown by this curve 2. So here, if we consider the voltage drop due to armature reaction, then we get the characteristic curve 2, which is slightly drooping as compared to characteristic curve 1. Now in this case, the load current IL and armature current IA both are same. So this characteristic curve 2, it is the curve between EMF E and armature current IA, which is nothing but the internal characteristic of separately excited generator. So this characteristic curve 2, it is called as internal or total characteristic. Now the curve of terminal voltage V and load current IL. So this is the characteristic curve 3. So this can be obtained by subtracting the ohmic drop IARA from curve 2. So the voltage drop in armature IARA, it increases with increase in load current IL. So as IL increases, IARA also increases. So if this voltage drop IARA, if it is subtracted from curve 2, so curve 2 minus IARA is nothing but the curve 3, and curve 3 is the curve between terminal voltage V and load current IL, which is called as external characteristic of separately excited generator. So this external characteristic, it can be plotted by performing experiment and actually noting the terminal voltage V and load current IL. Now from this characteristic curve 3, it can be noted that in case of a separately excited generator, the terminal voltage slightly decreases with increase in load current IL. So as load current increases, terminal voltage decreases. This is because of the voltage drop due to armature reaction and voltage drop in armature, that is IA into RA. Thank you. Stay home, stay safe.